Welcome to my video lecture. This is Amarnath, Assistant Professor in Mathematics, Department of Science and Humanities, MLR Institute of Technology. Under the course Linear Algebra and Calculus, I am handling the topic quadratic forms and related canonical form and properties. Let us see the overview of the presentation. Today's lecture. In previous lecture, we have discussed about the quadratic forms. Very clearly we have discussed it. What is a quadratic form? A second degree homogeneous polynomial is called quadratic form. And how to convert the quadratic form to symmetric matrix. Symmetric matrix in the sense A transpose is equal to A, such type of matrix, and vice versa. So generally quadratic form we represent with Q, that we are converted to symmetric matrix A, and vice versa means reverse, symmetric matrix to quadratic form. This can happen. This both we have discussed in the previous lecture. Right? Today's class, present lecture, we are going to discuss about canonical form. It is also one of the type of quadratic form. Means it is also second degree form, but only square terms will be present. So that we discuss. Now properties of quadratic form. What are the properties such as rank? What is the rank of the quadratic form? Index, signature, and nature of the quadratic form. These all we are going to discuss in our lecture. It is very important in the topic. And now let us define the canonical form. So we have one more name for canonical form called normal form. Sometimes in the examination they may call canonical form or normal form. Some authors also will mention as sum of squares form. Sum of squares form. Sum of squares form. Anything is okay. Means only it contains square terms, x square, y square, z square, or y1 square, y2 square, y3 square, this type of terms. We can call it as a canonical form. Then how to define? So for the given quadratic form, x transpose Ax, the quadratic form in n variables, x1, x2, x3, so on, xn. In the quadratic form it contains n variable. There exists a, for that matrix, there exists a non-singular transformation. Non-singular in the sense which is a det not equal to 0. X is equal to py, that linear transformation, the 1 degree variable to another 1 degree variable, that is x is transformed to y, that is called a linear transformation. So x transpose Ax into another quadratic form of the type y transpose dy. And one quadratic form we are, let us say, converting to another quadratic form. How can you say it is exactly not quadratic form? Quadratic form contains second degree and product terms, whereas our canonical form contains only square terms. That will be given by y transpose dy. Let us say y contains, I am taking 3 variable, y1, y2, y3. Right? D is a diagonal matrix which contains only eigenvalues. Let us say lambda 1, 0, 0, 0, lambda 2, 0, 0, 0. Just I am restricting for 3 by 3. It is similarly we can extend for n variables, y1, y2, y3, so on, yn. Eigenvalues lambda 1, lambda 2, lambda 3, so on, lambda n, the principal diagonal element. If you can multiply y transpose d and y, you will get, so y trans, let us see y transpose dy. Y transpose means the column vector becomes as a row vector, y1, y2, y3. Diagonal lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, and multiplied by y, which is a column vector you have taken, y1, y2, y3. If you multiply these 3 matrices, see very clearly y1 into lambda 1, lambda 1, y1 into y1. Directly I am multiplying 3. But actually we can't multiply 3 matrices at a time. First matrix into second matrix, the result will be multiplied with third matrix. Here I am writing directly lambda 1, y1, y1. That is lambda 1, y1 square plus lambda 2, y2 square plus lambda 3, y3 square. This is called canonical form, y transpose dy. So sum of the squares form. See, observe very clearly, it contains square terms, y1 square, y2 square, y3 square. Sum of the squares form. This is called as a canonical form. Right? Generally, suppose we have lambda is equal to, for a given quadratic form, it is converted into matrix A, and you got lambda is equal to 2, 3, 4. For this one, I can say directly what could be the canonical form means, that is we can write. That is substituting the lambda 1 plus 2, lambda 2 plus 3 and 4. That you can write as 2 into y1 square plus 3 into y2 square plus 4 into y3 square. This you can call it as a canonical form. Now, clearly depends on the eigenvalues, you will be having the canonical form. Just if you do the eigenvalues properly, then you can get the canonical form. But canonical form will be reduced in many methods, that also we discuss. Now, let us find the rank, index, signature of the quadratic form, that we are calling as the properties of quadratic form. Now, first one we define a rank, quadratic form. What is the rank means? Suppose x transpose Ax is a quadratic form. Generally, every time we are saying quadratic form means x transpose Ax. Now, in the matrix x transpose Ax, the A matrix rank will be the quadratic form rank, that is denoted by R. And in the quadratic form involved matrix, rank will be treated as a rank of the quadratic form. That is the one case. Means simply you can find the rank of the A and you can tell. In another process, how can we define means the number of terms in the canonical form is called a rank of the quadratic form. How many terms are there? Suppose let us say lambda is equal to, we got 2, 3, 0. So 0, one term is missing. Only 2 eigenvalues are involved. The quadratic form also involves 2 into lambda 1 square plus 3 into lambda 2 square. The 2 terms are involved here. So definitely the rank will be 2. So in 2 ways we can define quadratic form x transpose A, the rank of A is called rank of the quadratic form. Otherwise, when you convert into canonical form, then number of terms in the canonical form is also called as a rank of the quadratic form. It is denoted by R. Okay. Here 2, 3, 0, then rank is equal to only 2, because 0 will not be considered, 0 term. At a one row may be 0, at a rank is 2. Definitely the rank of the canonical form or quadratic form is 2. Right. Next property, index, which is denoted by S. The number of positive terms in the canonical form is called index of the quadratic form and it is denoted by S. The canonical form, how many terms involves in that one number of positive, only positive terms will be counted. That will be treated as a index denoted by S. Suppose let us say you got lambda is equal to 2, 3, 4. How many positive terms? 3 terms are there, 3 are positive. Then definitely S is equal to 3. Right? Because from 2, 3, 4 only we will generate the canonical form. 2 into y1 square plus 3 into y2 square plus 4 into y3 square. All terms are positive. We can say the index of the canonical quadratic form is 3. Okay? That is denoted by S. Next, signature. Signature of the quadratic form. If R is the rank, so already we discussed, S is the index, S is index, then signature of the S is the index, here I did not write, index, then signature of the quadratic form is 2S minus R. Okay, simply you want to say the formula, signature formula, 2S minus R, where S is the already we mentioned index means number of positive terms, R is the rank of the matrix. Simply this formula will generate signature of the quadratic form. Otherwise you can have one more thing, difference between number of positive and negative terms of canonical form is called signature of the quadratic form. Okay, number of positive terms, suppose example let us say lambda is equal to 3, 4, minus 1. Here number of positive terms is 2, number of negative terms is 1. The difference is equal to 1, which is called signature. See, signature. Otherwise, our original formula. Here, see, the rank is 3 positive terms. Next, index. S is equal to number of positive terms 2. What is the formula? 2S minus R. So, 2 into 2, 4. 4 minus 3, 1. So, both are same. So, directly straight away, you can use the formula 2S minus R. R, the difference between the number of positive terms 2 and number of negative terms 1 is 1. That will be treated as signature of the quadratic form. So these are the three properties we are discussing about. Any one quadratic form is given, you will be asking find the rank, index, signature. It completely depends on the eigenvalue and canonical form. So eigenvalues are there, automatically we write canonical form. From there we can say rank and how many terms are the number of terms in the canonical form. Index, number of positive terms. Signature, formula 2s minus r. If you don't remember the formula, you can say the difference between number of positive and negative terms. Okay, so this is their properties. Next, here we will discuss about the nature of the quadratic form. One more property will be discussed, that is nature of the quadratic form. A quadratic form is said to be, is it positive, negative, or any mixed, semi, that all we have. That we are saying positive definite. If all eigenvalues are positive, positive definite. Suppose lambda is equal to 2, 3, 4. See, all eigenvalues are positive, then automatically the nature of the quadratic form I can say positive definite. Okay, positive semi-definite. So, or negative definite. One more before that one, we have negative definite, same version. If all eigenvalues are negative, suppose lambda is equal to minus 1, minus 2, minus 4. All eigenvalues are negative, we say negative definite. Okay. Next, positive semi-definite. If all eigenvalues are positive, but at least one eigenvalue is 0. Okay, one eigenvalue is 0. That is lambda is equal to, suppose let us say 2, 3 positive and 1, 0. That is positive semi-definite, because all like 2, 3 are eigenvalues are positive and another eigenvalue is 0. Next, one more option. Suppose lambda is equal to 4, 0, 0. I said at least 1, 0. It can be more than 0. 2 zeros are there, 1 is 4 is positive. Positive semi-definite. Similarly, we can define negative semi-definite. If all eigenvalues are negative and at least one eigenvalue is 0. See, let us say lambda is equal to minus 2, minus 3 and 0. Two eigenvalues are negative, another one is 0. Or suppose lambda is equal to minus 1, 0, 0. One eigenvalue is negative, remaining are zeros. At least 1, 0 and remaining negative. At least 1, 0 remaining are positive. That is positive semi-definite, negative semi-definite. And indefinite, that is, we can't say particularly positive or negative or semi, we can't say. That all mixed cases. And all other cases, what are that? Some eigenvalues are positive, some are negative and some are 0. Suppose I have lambda is equal to 2, minus 3, 0. See, can I say positive? Can I say negative? No. Positive is there, negative is there, 0 is there. Mixed negative positive combination. Suppose negative minus 1, minus 2, 4. See, mixed combination. So that we can say indefinite. So based on the eigenvalues, these are all we are deciding. So all positive, positive definite, all eigenvalues. If all eigenvalues are negative, negative definite. Some are positive, remaining 0, positive semi-definite. Some are negative and remaining are 0, negative and 0, negative semi-definite. Now these 4 are not satisfying. Then combination is there. Negative is there, positive is there, or 0 is there. So we can't define particularly positive or negative. We can't say. That is called as the indefinite. Okay. So this is the nature of the quadratic form. So in the problem he will mention very clearly, find the rank, index, signature as well as nature of the quadratic form. This all purely depends on the eigenvalues. If you can find eigenvalues properly, everything can be answered very easily. Remember the definition. Sometimes they are asking the definitions also. Define rank of the quadratic form, index of the quadratic form. So very useful one, right? Next, let us do the one problem. So I have written here one problem. Identify the rank, index and signature and nature of the quadratic form. So far what we discussed, all the properties, is asking the one quadratic form. Can I say is it a quadratic form? Yes, clearly we can say quadratic form, because all terms are of the second degree, right? Remaining products are also second degree. So by finding eigenvalues, we can find the rank, index, signature, right? First of all, what is the procedure to find rank, index, signature? Means first of all, you must be able to convert the quadratic form to symmetric matrix, that we have discussed in the previous class. We know very well how to convert. Next, find the eigenvalues. Based on the eigenvalues, you can write the canonical form. Once we write the canonical form, we can declare the rank, index, signature and nature of the quadratic form. Now first of all, let us reduce the given matrix to symmetric matrix. Symmetric matrix which can represent above quadratic form, that we are calling A. Tell me how to write, how to do quadratic form to symmetric matrix. Very simple. First take the square terms, write the coefficients along the principal diagonal. X1 square coefficient 1, x2 square coefficient 4, x3 square coefficient 1, write along the principal diagonal. Next, product terms, write in the proper positions by dividing by 2. x1 x2 position divided by 2, minus 4 coefficient divided by 2, minus 2. So x1 x2 position is this one, minus 2, minus 2. Next, x1 x3 first row third column, that is x1 x3 coefficient 2, that is 1 1. Next, second row x2 x3 second row third column, that is x2 x3 coefficient is minus 4 divided by 2, minus 2 and minus 2. So 1 minus 2 1. See, it is very clearly symmetric. How, sir? That is a first row first column, second row second column, third row third column are equal. Definitely A transpose is equal to A, which is called symmetric matrix. So that we discussed in the earlier classes, how to convert the reduced quadratic form to symmetric matrix. Now let us find the eigenvalues and eigenvectors. So find eigenvalues. How to find eigenvalues? We know very well. We use characteristic equation. What is the characteristic equation of A? Det of A minus lambda is equal to 0. That is a quadratic characteristic equation of the given for the matrix A. Then we know how to do. So determinant, it is a determinant, subtract the lambda from principal diagonal elements, that is 1 minus lambda, minus 2, 1, minus 2, 4 minus lambda, minus 2, 1, minus 2, 1 minus lambda. Subtract lambda from principal diagonal, remaining elements are as usual. Very clearly we discussed in the eigenvalues and eigenvectors videos, right? Now, so this generally we can expand first row, we can get the eigenvalues, or I give one shortcut formula, that is lambda cube minus s1 into lambda square plus s2 into lambda minus s3, which is equal to 0. What are the s1, s2, s3? S1 is equal to trace of the matrix. How much that is? Trace means principal diagonal elements, 1, 4, 1. Principal diagonal elements sum 1 plus 4 plus 1, which is equal to 6. Right? Next, S2. S2 is the sum of coefficients, that is the cofactor elements of the principal diagonal elements. After leaving the principal diagonal elements, AD minus BC. So first principal diagonal element is 1. Leave that row and column, remaining det of 4 minus 2 minus 2 1. Next, plus second principal diagonal 4. Leave the 4 containing second row and second column, that is 1 1 1 1, plus third is 1. Leaving this third column and third row, remaining determinant 1 minus 2 minus 2 4. See, these all we discussed in the eigenvalues problems, which is equal to 4 into 1 4, 4 minus 4. Next, second one, 1 into 1 minus 1 0, 4 into 1 4, and minus 2 into minus 2 4. See, plus 4 minus 4 plus 1 minus 1 plus 4 minus 4, completely this is 0. And what is the S2 we are getting? S2 is 0. So here already we got S1 is equal to 6. Next, S3. S3 we know very well, that is a det of the matrix. Right? Det of the matrix, easily we can calculate. Expand the first row. First row means first element. We know very well it is a plus, minus, plus. Okay. So plus 1 into, leaving the row and column, 4 into 1 4, minus 2 into minus 2 4. Next, second element minus of minus, plus 2. Right, leaving the second column and first row, 1 into minus 2, 1 into minus 2 plus 2, last one plus 1 into, leaving the third row and first row third column, minus 2 into minus 2, 4, 1 into 4, 4. See clearly 4 minus 4, minus 2 plus 2 plus 4 minus 4, which is 0, and S3 also 0. Substitute in the equation. What we have assumed the equation for this determinant, lambda cube, right, minus S1 into lambda square, 6 into lambda square. Next S2 into 0, S3 into 0. So completely 0. Because S2 term is 0, S3 term is 0. Now take lambda square common. To solve this equation, it is a cubic equation. We have to get 3 roots, lambda 1, lambda 2, lambda 3. You can use a scientific calculator, but it is only 2 terms, easily we can solve. Take out lambda square common, lambda minus 6. So this product is 0, we have 2 possibilities. One is lambda square is equal to 0, and one more option, lambda minus equal to 6. That is a lambda minus 6 is equal to 0. Right, here lambda square is equal to 0 means it is a 2 times raised as 0. It is 0 comma 0 and 6. These are the 3 eigenvalues of the given matrix A or quadratic form related matrix A. We have doubt this whether eigenvalues are correct or not. We can check. We have a property, sum of the eigenvalues is equal to trace of the matrix. So see the sum of eigenvalues, 0 plus 0 plus 0 plus 6, that is equal to 6. Trace, already we have written trace, first one is the S1, how much? 1 plus 4 plus 1, that is 6. See, both are equal. Means our determined eigenvalues are correct. This is the one case. Now we got eigenvalues, then we can tell about rank, index, signature and the nature of the quadratic form. So let us see in the next slide. Right. So far for the given matrix, we got lambda is equal to 0, 0, 6. Right. 0, 0, 6 means now canonical form. Canonical form, that is we know lambda 1 y1 square plus lambda 2 y2 square plus lambda 3 y3 square. So already 2 lambdas are 0, we have only 6 y3 square. Okay, that is a canonical form. Generally I wrote directly here, that is a canonical form is given by y transpose dy, but here particular canonical form is not our topic. We want rank, index, signature, that's why I have written briefly here. Then rank R is equal to, so what is the rank R? Number of terms in the canonical form, only one term is involved, the rank is 1. Next, index is a S. S means number of positive terms, only one term. So 6 is only positive, 0 cannot be positive and negative, only 6 will be treated as index, that is 1. Next, signature, that is the formula 2s minus r. So 2 into 1, 2 minus 1, which is equal to 1. R, difference between positive and negative terms, only one positive terms, no negative terms, 1 minus 0, 1. You can define like this also. Right? Rank, index, signature. Next, we have nature of the quadratic form. Nature of quadratic form. Nature of quadratic form. That is, see, look at this one. Here, one eigenvalue is positive, remaining are 0. So, can we say all positive? No. So, positive along the 0. That already we discussed, that is positive semi-definite. So, one eigenvalue is positive. That's why it is called as positive, but remaining not positive, 0 is there. That we call semi-positive, semi-definite. Positive, semi-definite. This is the nature of the quadratic form. Okay, the quadratic form is said to be positive, semi-definite. So, this is a way to find rank, index, signature of the quadratic form and nature of the quadratic form. Right. So, one more problem here I am giving. Identify the rank, index, signature and the nature of the quadratic form. So here in the previous problem we have discussed very clearly how to change into symmetric matrix. So here I am writing symmetric matrix directly since we know the method. So first write the square terms along the principal diagonal 2, 2, 2. Next product terms, here xy term not there, 0, 0. First row second column. Xz, first row third. Xz, xz not there, 0, 0. Next only yz, the second row third column. That is 2, coefficient 1, 1. Right. So for this matrix we need to find eigenvalues, that is det of A minus lambda is equal to 0. So solving this equation, so already we know how to find the eigenvalues of the matrix, that we can say the eigenvalues here directly. I am writing here the eigenvalues for this one. Eigenvalues solving, we get eigenvalues here lambda is equal to 1, 2, 3. So here I am taking directly the without solving here, that we know how to solve the eigenvalues. In the previous problem we discussed very clearly, and in eigenvalues topics also, eigenvectors topic also we discussed. Now suppose solving this equation, I got the eigenvalues 1, 2, 3, 1 plus 2, 3, 3 plus 3, 6, that is trace. So briefly I am telling these eigenvalues are correct, 2 plus 2 plus 2, 6, trace is 6, sum of the eigenvalues is 6, so our eigenvalues are correct. Then canonical form, which we can write as y transpose dy, that is lambda 1 y1 square plus lambda 2 y2 square, lambda 3 y3 square. Lambda 1 is 1, lambda 2 is 2, lambda 3 is 3, that is y1 square plus y2 square plus y3 square, multiply with this is 3, this is 2, this is 1. Now one by one we can answer. Rank R is equal to number of terms, 3 terms are there, 3. Index, yes, number of positive terms, all are positive, 1, 2, 3 positive terms, 3. Next, signature, 2s minus r, formula, 2 into s, 2 3 ja 6, minus 3, so what is the signature? 3. So this is rank, index, signature. Rank means number of terms 3, index number of positive terms 3, signature 2s minus r, 6, 2 into 3 6, 6 minus 3 3, and quadratic form is said to be nature. Quadratic form is said to be all are positive, so we can say positive definite. Positive definite. Okay, so this is a rank, index, signature of the problem. So in this session we have discussed about the canonical form and quadratic form properties very clearly. Rank, index, signature, that all we discussed, and how to say nature, positive or positive definite or negative definite, that all we discussed. In the coming next video lecture we will discuss about a reduction of quadratic form to canonical form by orthogonal transformation. We have 2 methods to reduce the quadratic form to canonical form. I am going to discuss orthogonal transformation in the next video lecture. Thank you.